in Nigeria. We are again happy to have Professor Frank Doba from Germany online. Today, in the afternoon, we'll be having roundtable discussion. It's a privilege to have Frank online because the earlier indicated that they will only participate for 2 days. But yesterday, I discussed with him, we need to have robust discussion on this additive manufacturing, and he has decided to join us today, even during the discussion. So let us give him a round of applause. Also, for the round table discussion, I was able to discuss with one of us, Professor Olubemiga Olatidoye. He was in our faculty when I was a dean to do his sabbatical. And I also was privileged to visit in the US in June. I was in his office at the Atlanta University Institute Addictive Manufacturing. Right to have robots. It was the one that made the face mask for his university. So he will also be joining us for the round table discussion. So I believe with that, and those of us that have done, we will be able to have the robust round table discussion, and at the end of the day, be able to come up with policy direction as the case may be. There have been so many policies not followed, but we must do our own bit, and then we will know that we have fulfilled all righteousness. To share this morning session, we have here Mr. Emonike. Emonike is currently a Kano, the DP of the program. So, engineer overseeing raw material research and development council to share this session. Let us give the round of applause.
So thank you for this requested reaction. It's mentally also sitting for Mr. Habib. It's a privilege, and I want to do the part of Professor Odolo. There is no time to waste. Immediately, I think I should call on to that is Oloro Tomi Adeyeye and other is really
I think I should help you. Oluretomi Adeyeye. Now, when I do this thing, you are going to monetize.
Yes, no problem at all.
All right.
He will be presenting for us modeling and simulation of multi-dimensional thermal behavior of plates during frictions stir additive manufacturing. Dr. Olori, you are invited to the podium, and I hand you over the mic.
Good morning, colleagues, and senior colleagues, and our friends from the industry. I also welcome you to this morning's session. Okay. The title of our paper is modeling and simulations of the multi-dimensional thermal behaviors of plates during friction stir additive manufacturing. Okay. The overview of the presentation is on the next slide. Can you please help me? Hello? And so this is the outline of the presentation. Okay? So from the background of the study, the aims, the methodology, and then down to conclusion. Now, why modeling and simulation? Okay? Modeling, of course, is the representation of the process, a concept, or a system. Okay, it can be mathematical modeling, it can be statistical models, it can be game theoretic models. Okay, but why do we have to do modeling and simulation? This modeling and simulation provide the platform for observing, optimizing, and predicting the performance of behaviors of the process, concepts, and systems. Okay, you can see that somewhere and do a model. Others may be in the lab and be doing lab work. But when you're in the office, you can do some mathematical models and okay, the model can predict what is being done in the lab. So it has its own advantages. I will tell my students that every problem in life can be modeled, except spiritual problems. When I say that, one of our students said that we can use metaphysics to do that. I said, wow, okay, when we get there. Okay, so additive manufacturing uses data computer-aided design software. Okay, or 3D scanners, object scanners, to direct hardware to deposit material layer upon layer in precise geometric shape. Okay, so the purpose of our study is to look at the temperature distribution, layer by layer. Okay, as the materials are being deposited, what is the temperature distribution, the thermal behavior? As the name implies, this manufacturing adds material to create object. We are seeing that since we came here. Now, what is the process here? There are two processes involved, either the fusion-based or the solid-state-based. Our approach is the additive friction stir episode under the mechanical deformation behavior. So our work is to combine AN and then the friction stir welding. Is a combination of the two, and that forms the base of our study. Okay, next slide. Now, we can see the material, the plates are in layers, layer 1, layer 2, 3 to 5. And then you see the materials they have been deposited on the plates. Okay, so like I said earlier, it is a combination of the additive manufacturing and friction stir welding that forms the friction stir additive manufacturing process. And that's what we the model for in this study to see the material that is in deposited. Next slide. Okay. Now, the aim of this study is to develop a predictive model for the transient behavior in 3 dimensions of welded plates in friction stir additive manufacturing. And there are 2 objectives. I don't remember what we're doing this study. Number 1 is to develop a mathematical model for the transient thermal behavior in 3 dimensions of plates in friction stir additive manufacturing, to develop an analytical solution, and then also to investigate the effect of a material model. Of course, we also validate the model using some experimental results. Okay, so we see the process here. As the sugar is moving, there is depositing the material. This is a friction stir additive manufacturing process. And this is a schematic diagram. That's the way it works. The heat input from the rotating tool pin is simplified as a time-dependent point-moving heat source. So the moving point heat source moves along the plane, and that's what we model for. Now, we start with the Fourier law of thermal conduction. That is equation 1. You can see that it is transient and is a 3 dimension, even though a linear equation. But by the time we look at the boundary conditions, we see how it becomes complex and the method we apply in the solution methodology. Okay, we see the parameters used there, the initial condition because it's time dependent, and then the boundary condition. Okay, we have the parameters, they are defined, QP is the mass supplied by the plane. K1 is thermal conductivity of plate 1, because we have several plates, plate 1, plate 2. So we're going to look at different conditions. When we have perfect thermal contact, and when we have a perfect thermal contact, when it is time dependent and when it is not time independent. Okay, next slide. So there's some basic assumptions here. The first one is that the workpiece is homogeneous and uniform. The material properties are uniform in all directions. Okay, the boundary conditions of the thermal behavior are symmetrical. In other words, to X to Y is symmetrical from the center line during the manufacturing process. The thermal properties of the workpiece are constant. There is no phase change during manufacturing process. The major heat source is also constant. That's our first assumption before we now remove the assumption. So for case 1, we assume that there is perfect thermal contact from layer to layer. No heat input, no heat exit. It is contact. And then case 2 is when we have imperfect thermal contact. Case 3 is when we have imperfect thermal contact, and it is also time dependent. We're looking at a transient deformation behavior. Now, if there's no heat inflow and there's no outflow of heat for the workpiece at melting temperature of the material. Okay? The heat generated at the moving point heat source and workpiece interface is considered to be invariant with X and Y. In other words, we have said that it's symmetrical to X and then to Y. So there's no variant of the heat generated there. And then the heat exchanging boundary condition between the workpiece and the top surface now, and surrounding is that of convective and the radiation condition. So we have conduction from the plate and then convective and then radiation. And so we have that equation there. But because by the time we're doing the modeling, the radiation term, was becoming very, very complex. We have to linearize and reduce it to conduction and then convective. Next slide. Now, since we have different plates, for the top surface and the second plate, we have this condition. Okay, the conduction and then the convection. And then we have several plates like that, several plates. And it gives us this summary. You can see the I there. The I represents plate 1, plate 2, plate 3, plate 4, like that. That's equation 6. Now, however, if there is perfect contact between the plates, thermal contact, then we have this. Okay, that means that in between the plates, there is no heat loss and there is no heat input. It's perfect thermal contact like that. And so we have equation 7 that summarizes that for us. Okay. Now, at the bottom, we're talking about the top surface. And then at the bottom, heat is lost by conduction. And the model, for the model, for support, and the base is complex. Okay, sorry. At the bottom surface, all our work is heat is lost by conduction, and the model for support base is complex. Okay. Now, but in order to overcome the complexity of the model, we made this a conduction condition. Because the bottom surface will rest on everything. But we assume that it is conduction. Okay. And that gives us equation 8. Now, for all other boundary conditions for Y, for Z, we assume that they have the ambient temperature. Okay, next slide. Now, going through equation 2 to 9, when we substitute into equation 1, we have a very complex equation. Very complex, and we resulted into using this method, differential transform method. It is a very good method for linear and non-linear differential equations. And so, and because it's a 3D problem, a transient 3D problem, we use the 4D differential transform method. And that gives us, we have a summary of the transform in table 1 and table 2. This is the differential transform method for 1 dimension, and then the next one is for 4 dimensions. This is for 4 dimensions, and that was what we adopted here. Very complex, but we're able to simulate using the MATLAB workflow. Now, for this study, this is the first time we'll do this study, we've not done an experimental study on this. So what we did in order to validate our work, one thing is to develop the model, but if the model is not validated, either by the numerical method or more importantly, experimental method, of course, you're just doing it at all. So what we did was to compare our results with what had been done. Somebody had done the work on aluminum alloy, and he used the friction stir welding. And since our method is from friction stir, we just compared our result. And we discovered that our results, maybe not perfect agreement, but in good agreement with the experiment. You compare it, we pick the points at 11 millimeters on the plate, 15 millimeters on the plate, 17, and then we have that, though not perfect, but good agreements between the two of them. And so we now look at the temperature distribution. So figure 4 is the temperature profile for different depths of the material from 8 millimeters. So what we did was to pick X at 8 millimeters and then look at the depth. Okay, the depth, which is Z at 8 millimeters and then the depth. And so we have this result. You see that at 8 millimeters, we see the temperature is over 8,000 degrees centigrade. Okay, and then for this, what we did was to keep it at 8 millimeters and at 16 millimeters. So we have that duration to there at 8 millimeters in X and then 2 millimeter depth, that is Z. And so we have that result. So the next slide. At this point, what we did was to pick at X. And then we compared the at 0 millimeters, 25 millimeters, 50. We observed that there's a rapid increase in temperature. Okay, as it moves, and there's a rapid increase in temperature towards the pin point and slow decrease while we drawing from the point. In other words, as the moving point, each point is moving, there's a sharp gradient, a high temperature gradient at the front of it. And then after it, because it has to cool down, there's a sharp gradient here, and whereas after the moving source is not as high as at the point. Okay, next slide. Okay, here we look at temperature profile of these at different widths of the plate. At Y because 25, 50, 75, 100. We look at that. We did it for Y25, 50, 70, and 100. Here is plate 1, plate 2, and then for plate 3. We're looking at that. Since we said we have a perfect thermal contact between the plates, the results are almost the same because that was the first thing we will consider. Perfect thermal contact. This is for plate 1. Okay. Again, this is for plate 3 and then plate 4. Next slide. We also did a 3D plot for this. Okay. We did for preheat and then without preheat. Okay. For without preheat, we put the temperature at the middle of the plate and we have this profile for the 3D. We've already done the 2D and then we're also doing the 3D. Just look at the different points. And then for this one is without preheat. We pick that 25 millimeters from the edge of the plate and we pick the same way. This is the preheat. You see that the peak temperature is higher here than at this point. Okay, figures 12 and 13 shows the maximum temperature of the material without and with preheat. And then figure 12 shows that the cooling rate is faster. Without preheat, the cooling rate is faster. Whereas with preheat, the temperature increases, the peak temperature of the material increases. In conclusion, in this study, the analysis of three-dimensional transient thermal behavior of bodies processed by friction stir additive manufacturing is studied using DCM, pressure control. The obtained results from the simulations for various observed points show typical features of the temperature profile, and this provides critical analysis of the factors influencing heat flow models in a moving heat source. Hence, the Dow model and its analytical solution provide the benchmark for obtaining temperature profile in a point moving heat source during additive manufacturing process. Okay, next slide. The paper we compared our results with is the paper published in 2017. That's just like I showed earlier, that though not perfect, was a good agreement between, so the all other references are in the manuscript. Thank you.
We have a breaking transmission. Anyone here available? This microphone, they respect us. Thank you very much. We have done a very wonderful presentation on modeling and simulation of multi-dimensional thermal behavior of plates during friction stir additive manufacturing. So, we take a question. So, any question for him? Yes. Yes. I want to see all those who have questions. I don't want questions to come. Number one. I think number three. Number three. Okay, number four. Yeah. You have not really stand up the company. Okay. Yes, number one.
Nice. Please, I would like to be specific in terms of your difference in the results and that what do you mean by your experimental results? Your experimental results and experimental
But we had to agreement between what we did was no one had done, for example, that.
I want to take all the questions. I want to answer those questions. I thought you can simulate these answers.
Okay. Yeah, for the experiments, at 11 millimeters, the temperature was 306.9 seconds. While for the module, we got 298.5. We have not the percentage units.
I know very well. Number two.
Number two.
Like heat source, you can never be as spherical or overhead. Then I'm very strong. The previous programs also can very, very strong.
Because we're already working on the second page. You know, I told us earlier that we have the case one we did was for perfect thermal contact. But we're going to relax that condition and look at the revision. Maybe that will give us the data answer that we have. If maybe if not or if inputs, as the point is moving, there may be heat input, there may be heat loss. And that will account for the difference in the so we're going to phase 2 and then for phase 3 when we'll consider time dependent behavior.
Okay, number 3.
I have 2 questions. The first question is the budget condition. The first one now T at 0 is 0, the temperature is 0. And T at X and Y is 0. They are T naught. Therefore, the T is constant.
That's an assumption. It's constant.
But it's not a real life stuff.
No, we are assuming that there is perfect contact. Yeah, so that's the result.
Secondly, the material properties are actually address properties.
Yes, we use the aluminum alloy and all the properties of that. It's our property. And then all the properties of the material are there.
That's the
No, you didn't say
because I was saying that actually
yes. No, I said we use aluminum alloy, and then I gave the specification of the material. It's like the
Okay, that's fine. Naturally.
I'm not the one saying that with us.
That's why. You are number 5. The other is followed.
yes.
Why?
But my question is that
I would like you to introduce yourself because you are before the answer. The other ones I see you have not been
my name is So my question is on the equation. How do you measure from the book? Now you show the table. Is it that the table is a standard table that perhaps the expressions are just doing, or what that you can tell us what you have just said? Is it the table standard table or
It is actually, before I reviewed over this time, it was developed to transform the perfect relations. And not in equations, complex equations. And then we have tables developed over time. Some of them have been put in textbooks, some of them are coming up with new, like the form DC is a new one, and they're even very complex, but we can handle any multi-dimensional one. So it's a standard table that the developer proves.
and you mentioned that's
Oh, I sorry about that.
Are you okay now?
and you because it's also
So,
no, it's just for
it's just for you to take correct some of these things. Dr. Sharma,
thank you very much.
yes.
Thank you for the information. You have I should have better
Your assumptions. One thing for future weddings is the assumption that this is solid state. However, in reality, based on some of the experiments we have done, it's not actually a solid state. It's not a purely solid state process. So, at the stage where two material reach the highest level, they are found from my side evidence of input. So the process is not perfect. I've not seen you incorporating that assumption in all which may make the result very far from actual. That's what.
So thank you very much. So consider that in the study. We do mathematics. I said we do mathematics. Try to put there. So we're going to consider that because we don't have case 1. By the time we go to case 2, case 3, all these assumptions will come in and it will make the model more robust. So we
similar events.
Thank you.
To me, this take note of all the techniques or corrections they have done so that we can have it effect. Can we give you a round of applause? Yes, we now take our second paper. So, I think I will have to take the second paper. Our second paper is coming from the Department of Mechanical Engineering, Addictive University. We have
online.
Oyetunji, it's online.
It's online. It's online. Yes, it's online.
It's online. Dr. Oyetunji, you are on. Bring him up. Bring him on, please. He's presenting the paper on a comparative study of 3D printing materials. That's the PLA and APS mechanical properties via simulation using COMSOL metaphysics. Okay, is that him?
Right, good morning. Can anyone hear me? Okay, so I'll share my screen now. Okay, so my name is Oluwaseun Bolaji, one of the author of the paper, which is titled Comparative Study of 3D Printing Materials, which is we have the PLA and the ABS, the mechanical properties via simulation, using COMSOL multiphysics from the Department of Mechanical Engineering at University of Technology. So first, what is 3D printing? We all know before that 3D printing is a three-dimensional printing in which you can see the height, the width, and the breadth of everything that we drafted in our computer-aided design tool. And 3D printing has grown in popularity as a method of developing tools, functional parts, particularly in industries. Also, it's not so uncommon among hobbyists, research and design, and other people as well. Also, aerospace, and mostly it's used for prototyping. I want to get things done as quick as possible. Now, because it is so popular now, because we have adopted 3D printing as a manufacturing tool in industry, researchers have been considering it, whether it might one day replace the conventional injection molding when it comes to plastics, or the casting when it comes to metals and some other manufacturing process. And that is why work has gone into experimenting to know most of its mechanical properties and to improve on them. When it comes to knowing mechanical properties, sometimes we know that it comes with destructive testing, and it leads to waste of material, testing like tensile strain test and all other mechanical tests that we know. So in this work, we employ the use.
If you can hear me, can you put it on a slide mode?
Okay. Okay,
that's
all right. Okay, thank you.
Thank you.
Yeah. So in this work, we employ the use of COMSOL multiphysics. We know we have other materials apart from PLA, which is polylactic acid, and ABS, butadiene. We also have metallic alloys as well, in which we use as a material in 3D printing. As a 3D printing, additive manufacturing, We have other process apart from fuse deposition modeling. We have selective laser sintering and all other ones. But for this paper, we've employed the use of comparison between PLA and ABS. And we use a virtual environment. And like it was rightly mentioned the other time, there is nothing we cannot model except spiritual problems. So we were able to use this virtual environment to model. And what that means is that we are not physically destroying materials. We are actually doing everything on a software, which makes it to be cost effective. And so what is Console Multiphysics? Let's start with that. Console Multiphysics is a software platform through which we can model real-world physical designs and processes in a virtual environment. So physical design, talk of fluids, talk of electromagnetics, heat, structural designs, chemicals, acoustics, and even we can even create a question by ourselves, which makes the software very flexible. It is also optimized to our needs. And we can also import from other tools such as MATLAB, Simulink, Excel, and CAD integration, computer-aided design software such as um, SolidWorks, such as Creo, and other ones. So we have the application of it as we can use it as a modeling tool for in aerospace, in other fluid mechanics and dynamics, and in other physical areas as well. You can also use it in software user interface when we create our software and reports on top of histograms and all other charts that we can think of. So this is Console Multiphysics. And so in order to use in our paper, in order to use that Console Multiphysics, the methodology that we've employed is through the use of the von Mises stress analysis and displacement, in which we were able to study in two different direct load application process. We have the simple supported beam and the cantilever. Those are the two cases that were taken into consideration. So the first thing we did is to model the flat plate in SolidWorks. So we built the plate in SolidWorks, and the dimension of it was 100 by 10 by 0.5 meters plate. So we modeled it in SolidWorks. And so if we look at the second interface here, we were able to create adequate definition. What that involves is we create the parameters of the component to be modeled. And these parameters will be strictly created in the wind. If you look at it, we can see electric current, its transfer in solid mechanics, and we can also see some other ones. So in this, we can see we choose solid mechanics, which is the parameters for our plate. And if we see, the other thing that we were able to do is to create the research material, to specify the research material. And this involved the use of built-in parameters. So the parameters is already built in the software. And we created the parameter in a blank material option. So if we look at it here, we can see an example of it. We have the ABS material. So the other material that we can also create is PLA that we did here. So these are the material creation. And also we mesh it. If we recall, when our 3D printer is printing the material on the hot bed, one thing that we see before it covers everything before finishing is some mesh and some interlockings. The 3D print, the software was built in the sense that it will create the material to be more to have less weight and to be more stronger than other material. So we were able to define it inside the software as well. If we look at the other diagram here, we can see as it is being simulated. So we can see the displacement field result. We can see how the material is being displaced as well. And this is involve the use of this process for each of the solid mechanisms physical to be studied. And so that is how it is being done. So if we look at the last diagram here, the stationary study frame. So we have to define the environment in which the material has to be. Talk about the temperature, and we know that these materials, they are temperature sensitive. PLA has a lower temperature than ABS. And so what are our results? What we were able to see here is that if we take a look at this graph, this is a graph for PLA under a simple supported model, and this is a graph of ABS under a simple supported model. And one thing that we can be able to see is that this side, we can see that PLA was able to withstand more stress than ABS. If we look at this side, and if you look at this side as well, and in comparison with this side for ABS and also this side for PLA. Now, what that means is that PLA is able to withstand more bending and more stress than ABS. And ABS actually is harder than PLA. And this, when it comes to hardness, this sometimes doesn't define the strength of a material. They can head, for example, or a glass. A glass can withstand scratching and can withstand other impacts to the surface, but which is quite different from a rubber band. If you look at it, the rubber band can be stretched for a longer length before it exceeds its yielding point and it breaks. Also, the cantilever supported model for the PLA and the ABS. If we look at it again, we can see that the PLA was still able to withstand more stress than the ABS. So what does this mean? What it means is that although PLA, in conclusion, PLA and ABL models were supported and at different head, it might be 1 or 2 end, they will experience poor ductility and are liable to break more easily on application of low stress. Take for example, I put a plank on two supports of blocks, and then someone sat at the center. So that means the plank is liable to break under 1 or 2 support. And also the use of PLA provides more ductility property than ABS, although not too high, not too much, but it provides even more than ABS. And finally, there is an adverse effect on the strong property of ABS when in use over PLA. So those are the comparisons that we're able to make in the case of PLA and ABS. So thank you so much.
Thank you, Dr. Matuji. We'll be taking questions from this side. Are you still there?
Yes, yes.
Questions from this side, Dr. Matuji?
Okay.
Yes. Okay. I give you the second microphone.
Thank you for the wonderful presentation. The questions I have is the property that you have investigated. Is it not possible for me to know those properties without simulating them? For example, we are considering PLA and ABS. I'm a civil engineer. If I consider the property of steel and concrete, I can tell you without going anywhere what the reaction will be when you subject it to root. Because what I can see here, you have a cantilever and you made them with PLA and ABS. So if I make a cantilever beam of a steel and a concrete and I apply load to them, I can tell the one that will do better. So what is the difference, or what are you trying to achieve by these simulations of having the displacement functions and the strength parameters, since from the physical properties, you can easily determine all those things.
Bolaji, did you get the question?
Yes, thank you.
Please don't freeze.
Materials. Yes. Hello, can you hear me?
Yes.
Okay. Sometimes I tend to do some things like that, but you know, as engineers, we are inquisitive and we tend to want to know things and to also apply equations on them. In this case, we were able to use von Mises, and although we are not being mentioned, we have some parameters that we were able to gain from it. And in the case of the maximum value of the simple supported and cantilever support, we were able to model to get the results, which is 50 kilopascal and then 370 kilopascal respectively for both the simply supported and the cantilever. And also, if you check the other graph, we also have a stress value that was deducted for ABS and for a simply supported ABS and simply supported PLA. For PLA, we have 47 Pascal, and for ABS, we have 350 in terms of the result that we're able to get. So what that means is that let's say we print a material, let's say for example PLA, and then I print the material for a chassis of a car, and then on the chassis of the car we put some things there. Let's say the battery, the computer, the load is also being supported by the tire of the car and all other things. So let's say from the two ends of the tire of the car, what it means is that if I'm able to get that value, I will know the kind of load that I'm able to put there. I will be able to quantify this is the weight that the battery should be, and this is the way that the other components should be, that I will be able to place on the car. So those are what the values that we're able to get are used for. I don't know if I communicate the...
Without simulating it. Okay. Are you curious your hand or your stretching? No other questions? And if there are no other questions, can we give me a round of applause? With that applause, we come to the end of the first session here. We go for tea break, and after that, we take the remaining 50,000 before we have our round. Is that okay with us? Yes. Prof, do I have your permission on this?
Wow.
Thank you, God bless you.
Yeah.
We are taking our next paper of today, effect of energy density on corrosion behavior of additive manufacture in world promote chrome alloy. This is a paper by Oshoma L.O., Oladoye A., Ololusho C.O., Abiodun Y.O., and Abene B.O. From the Department of Meteorological and Materials Engineering, University of Lagos. I don't know who is presenting. Is that what? Please, while I invite, okay, Dr. Shoma, you told me already, while I invite you here, I will crave your indulgence. It's your phones on silent phone. That is international best practice for presentations like this. You might look at the people here, the number might not interest you, but the quality is very high. Let's keep to that quality. God bless you. Dr. Shoma. Why are you sweating like this?
Thank you very much. And once again, I welcome all for this possibility that concerns team and control in the University of Lagos. Actual presentation is energy density composition area of teamwork, mobile group. Fortunately for today, I'm having a lot of presentation. Sorry, also, is it not possible to change the slides? No. For the purpose of actually, you know, okay. No, he has fixed it perfectly. He has positioned it. Thank you, sir. Well, I said this is a lot of comfort and not feel the component of this. I have some components produced from this particular research, and another one, the wire mesh that's built by the that's the outline of my presentation. So I think manufacturing the technology is very substitute for rapid manufacturing process. and that will recognize and revolutionize the industry processes to a very short while. Parallel verification process is one of the methods of additive manufacturing using powder form to produce metallic parts directly from 3D models using either linear or electronics. In this current one, I was privileged to have worked with this precision ADM international manufacturing company in Canada. We use the supplier customer manufacturing parts to meet some of the challenges of part placement. So precision ADM, they have used powder verification process using direct metal deposition to produce component parts. Started using aerospace, military, and application. For this particular material, I will use mobile command. The challenge of that company at that time was that for their team work in this material, they are having a problem of porosity. And customer has been complaining. So the challenge for us as a research team was to simulate the teamwork product and assess the level of porosity and if the material will exhibit some that has been seen from the industry. So this is a continuation of the project. Some of the results of that project have been presented. In the previous project publication, we have looked at microstructure and mechanical practical mechanics. However, in this particular investigation, I'm concentrating on the ocean stability of this area. While others experiment was carried out to analyze in Canada, this particular one was analyzed in so the objective is to complete the just 79 of microstructure arguments and position of this area. And that will help people better understanding of the effects of the dynamic density on the corrosion parameter for this material. So we have cascade. So we have cascade design energy density processes that essentially have low energy density. We have the recommended energy parameters from the industry. Oftentimes when you buy this powder, the original manufacturer will give you parameters that they consider as optimal to produce them. So what we did was to vary this parameter in between the recommended energy density parameters, going to the high and the low density parameters. You see that. So under for additive manufacturing process, one quality check or process that is normally used is what is called P, known as hot explicative press. In essence, is to apply heat and pressure simultaneously to be able to reduce the effects that's commonly attributed with through a combination of passive installation, creep, and addition. So these are the experimental parameters. I have a packet nice which varies from 12.2 and 7.4 and 3.89 and 7.4 meters for both low energy density and recommended energy density and high energy density. The power and the speed varies within this range. Irrespective of this should classify as either low density energy, which is 0.5. This is close to the recommended energy density. It's a higher energy. This is the difference of the. So, in doing that, for the energy density, standard formula is power over voltage, the constant. That's very good. Also very good power. Power, very good. In corrosion, we use standard weight loss immersion test. Over a period of time for 5 days, while we measure the weight loss at the time of 2 days. This was also validated in the correction test. And these are the parameters that made it. So, this is a typical in all 150 that was prepared for ISO and this is design of future design. At the end of the laser deposition, part of this, that's why we have those samples we really have for the government. And all of them, because of the failures, the 150 sample have unique power density relation. So at 150 parameters, that's repeated both for the abuse and so part of it is what I'm using for this current experiment. So this is typical as built upon. That's what you are feeling. When you go somewhere, depending, as I said, you are all numbers. So that will be high energy density, this is recommended energy density, and this is low energy density. From the surface appearance, you can see evidently there is difference, even though the difference is the same. This is analyzing looking at the optical image as expected of as being and it has a lot of different, especially because and we can see from the recommended analysis that the lowest velocity, the high analysis has the highest, and the low analysis is intermediate. This is using standard recommended to high analysis. You see the nature of it. Especially, they are incomplete narrative of the houses. Can you see that? So, quantify is part of what I've reported in the first illustration. I quantify the volume factoring of this defect using the J analysis. And I found out that, irrespective of the material, the recommended energy density actually produces the lowest defect, while the higher energy density is higher, even the lower energy density is higher. So the difference appears, I very respect of whether someone because one is not consistent, the other is not consistent. Furthermore, after eating, the process which I've explained, what I noticed is that the effects of that active condition is actually neutralized or normalized. That's significantly after eating for this time. So, however, eating has greater influence on the iron density and the low energy density more than the this is instructive. We say that for the low energy density, the speed is actually more faster, which means production rate can be enhanced. Furthermore, this result, these are as big as these are big, and significant reduction in this found. This is the cross section of that. So this is the cross section. So this is the cross section of those samples that have in optical form. You can see the layer by layer division of the internal form. So, and as I have mentioned, you can see the major difference between these all these are just the passes of the base structure. The solution the base. So whereas the project one is very final than the high level density, whereas the low level density is more final. But after evening, So you can see that the microstructure is essentially organized. There's no relation to whether it's ILM or medium or similarly in another relation to the. So what is the summary from this investigation? We also look at the environment. This is as built, and this is and see after it, there's organization and there's no relation whether using material in an information or after it. So, coming to the corrosion, which is the main essence of the manufacture, we also found out that the corrosion stability of this material, either in high energy basis or in low energy basis, is actually a function of or depends also on the energy basis. For low energy basis, if the thickness is high, that is 0.8, those ones that close to 1 millimeter, the corrosion of this is relatively lower compared to the one that are similar. Also, the recommended energy density appears to even be more sensitive to corrosion than the low energy density and the high energy density. Similarly, combined effect of thickness and the energy density shows that just as the formula shows that the functional is equal to functional thickness, as the higher the thickness, the lower the process. So, and we found out that both the as built at low energy density, as well as the as built at high energy density, actually have relatively higher corrosion resistance. So, therefore, we further investigated those particular things using the to confirm this particular which is faster procedure, and the result is what we find out that for the as-built high energy density and the low energy density, the high energy density actually have lower corrosion resistance compared to the as-built low energy density. Whereas this is the energy density of this is much higher than this. However, the corrosion sensitivity of the higher one is still lower than that of the lower. However, the same parameter, high energy, low energy, if low energy and as low energy, if have a better corrosion compared to the maximum. So this is the table of the corrosion parameters. And see, the energy is between these and these, different, even though the energy is. So conclusively, that some of the previous information, there's no microelectronic integration, the mechanical property of the low energy that used and compare favorably with the recommended one, and can serve as a substitute to the recommended baseline precedent. In view of the fact that the production, the productivity using low energy density can be faster than the recommended energy density. Also, post-spectrum treatment, if designed to reduce this, is much more effective for the high energy density and low energy density than the recommended energy density. But for on the effect of corrosion, yes. So, some of the areas of the copper alloy, the higher the usability. The susceptibility of the recommended parameter for the acute copper alloy is higher than both the low energy and the high energy, irrespective of the areas. The same thing is applicable to G. So, corrosion density of the acute high energy appear can be compared to the low energy if samples, even though the energy density are similar. And at comparable energy density, the corrosion stability has built low energy density significantly higher than if
recommended low energy density pumps. So finally, what I found out generally is that while EPIC is a statutory requirement for quality, it also has a fair contribution to stability to the country. And that for AM component, in something that can be applied where the certain requirement is not too critical, and with America or sales company. The AM component can be applied something without post-production need. That is without incurring higher costs. That's my conclusion. And this is consistent with key periods and the key periods finding. Acknowledgement to all your information. Thank you. And I was Professor, you say your energy density is also high. A lot of stress to the camera and kept chasing you from here and there. That is high energy density. Questions? Yes. You will get an award for first shot.
Thank you, Dr.
Yes. And just a moment before you get your question, I want to get through my numbers. Bro, I'm giving you my second shot. We are number 2. Number 3. And then we take 4. That's it. We're not doing that. There is anybody? Okay.
My questions begin with those. I'm so glad that it is the department. What do you mean by aspirate? And I find out that the key one is better than that of aspirate, correcting the effect of the defects that we understand, looking at all this velocity and feelings. Do you, if as a micro as the small part, or if I have the material, because I'm a civil engineer, I understand. You see, when I'm cutting all my material before, can I also keep that material if I find out that there are defects in this material? So is it possible for me to heat the material in order to correct the defect that I have, or I have to go into the microscopic before I can? Okay, that's one. What is the effect of energy density? What's the property? What will I achieve if I have energy density in what information I expected that I should have? To have high energy density. What is energy density?
I've defined define energy density. That was the formula. Energy density function of power over speed. I pass around with that. We are discussing the layer by layer condition. So that build additively, that is, they are shown to us in the book of the video that we watch. That's the way we are doing. So layer by layer in question. So when you produce it without it, that's high heat.
Okay.
So when you now and anything you ask for this energy, that is processing parameter, power over speed. So depending if the speed is very, very high, very high speed, definitely the energy density is low. If the power is not that can increase it, then maybe the energy density is high. As I said, for this one going to power. I mean, I remember that always recommend optimal capacity so that the demand. So what we have done is to vary away from those to analyze some other things. And as I have seen from the conclusion that I have shown, irrespective of the way you produce the value. However, consistent with the recommended energy parameter are the lowest. But after eating, that effect is no longer.
What is it? What do we do? After finishing,
I define
after treatment.
Yes, I said, all participating person is a post manufacturing procedure that reduces, I can see the procedure there. Put it in very high pressure containment pressure and sometimes now and 45,000 liters. So what do you want to achieve? You want to achieve a picture of heat and pressure, etc. On those components of the so first that you can use those data that are saying now. Which is where everybody show after eating this component. Those people nearly not only in our life, also have effect on the environment. The environment is essentially what am I trying to do about it? If not as such sensitive enough, maybe or for why going to recommended elements when you can produce faster using the elements and see achieve if you are going to do. So I now went further to look at that effect also on the motion and also the result was consistent. That's just
Thank you. That's all. I have to comment and one question. The first comment, which is basically an addendum to this, is that in material science, whatever post-processing technique is basically to enhance whatever property you have generated as. And except that material, that product is put in service, it is considered that the OEM, that is those people who call original equipment manufacturers, they will have done their R&D and they check that this is the best way to go about it. So if you are doing HIP, whatever other process, basically depends. You are compressing, which means you are including probably lots of clean items. Or you are doing what we call micro welding. And that is where my question comes in. The HIP has a limitation. What it does is to compress the grains, then resolve the defects. But what is the maximum defect size? Because if it is too large, okay, it will not go. It will not go. So at what level of deformation pressure, or what is the size of effect that you generate that we ensure that if you take it through HIP, it will normalize as we have seen. Otherwise, HIP is an additional process. So it's costlier. You have to the machinery, the tooling. Why not just work around the OEM design parameters and save yourself the extra cost, the tooling, and what have you. And on the issue of indifference in micromagnets, it is expected because you already normalized the pre-history of the material to cancel it out by HIP, except some other things. So the question is, what is the size range of the defects that will encourage us to go for HIP? Thank you.
Thank you for I would say that was outside the scope of Actually, I used to do analysis to characterize the volume percentage. However, what I mean by volume percentage, that is what's the financial difference we have in this condition compared to not the size. They will be bigger and fewer, Or they could be smaller and many. So, but that was not beginning of what I study of standard, you have to know what size of those things can actually affect the material or can affect the use. Actually, so it's important. I think it's raising a very valid point. So if you go there, you discover few of them. They might be few and big and very small, and they might affect the effectiveness of the material. Yes, hello. I'm too. I am not there. Yes. So I was. I tell you the difference between 0.3, 0.03, 0.035 to 0.04 inches. Let us pick one. So the maximum was 1.1. Then that's right. 1.1. And actually, based on like general fashion, actually produce layer by layer. Yeah. I want to ask you a question. I want to know the relationship between the number of layers you need to achieve that, and how can you improve property? I don't know if you are getting. If I want to achieve 1.1 mm, and I have to do it layer by layer based on my function, how would I determine that I need this number of layers to move to achieve that? For example, let me just say this. Maybe I just need to understand that if I just do 3 layers, if I just do 3 layers now, what enhancement would I have if I go to 4 layers, if I go to 5 layers? And if we can determine that, then there should be a point where we have to know the optimum number of layers for the optimum thickness. I don't know if you can clarify that. I'm is actually a big thing. So that will design already. That's the next. So what did you do? And you're already programmed. Okay, still this from my sorry, that's a design layer. Yeah. When I was going through some papers, I saw some additive manufacturing based on 3 layers. I saw some based on 4. I saw some based on 5. So what parameter do they use to know the number of layers to achieve a particular thickness? That's what I'm asking for. I don't know what I'm saying is that you have 10 mm. I can go 2 layers, 5. I can also go 3 layers. In additive manufacturing, the only parameter for that is the energy density. There are other parameters that should go. One of them is called the hash length. Hash length means it's just like when you're doing your solution, your stepwise. So I stepwise. But you know, the higher your stepwise, the more volume of the metal you're depositing, and the more chances. So definitely, what I'm going to do is to make sure that a slower or a tiny step, so that the material can be refined. If there's any opportunity in the previous one, when the new forms up, it will make it homogenize it and solidify. So, however, if you have a higher aspect, what you're going to produce is material more. So, I did not look at the effect of aspect in this particular. Just material evidence. That's not the only factor that affects aspects of that. And it's a straight teamwork. Normally, the material want to without various registers and angles. So even angle of the mechanism are factors. So you said you produce layer by layer. Yes. How many layers? I told you, this particular one is simulated. The program is and you print it out. I don't know. Okay, no problem. The second one is a suggestion. This is of figure 10. I just want to suggest. No, in the slide. Are you like me slide?
So I suggest when the figure is like that, just take me more money like on this figure now, just have 1, 2, 3, 4. It's better to be second take one version. This is not figure. Something like this, you must have more data points for you to have figure. But for something like this, it's just people or charts. So the same thing applies to figure. It's not a suggest.
Noted. But if I what we are looking at here is just the accuracy. Intermediate or recommended and high.
Yeah.
Okay. Thank you, Chairman. Thank you, Dr. Shoma. Thank you. Your response to Dr. Shoma, we talked about the position. I'm also grateful that actually brought up the field because the steps are too large. The steps are too large, like error. So if you have 5 steps, then you will have second to the last figure, that observation. Can we go to the second to the last figure? And we don't study the second to the last. Yes, second to the last. Please. I see that in this figure, it appears to have so many data points because now you have appropriate scores. So in this figure, we are varying potentials versus current. So perhaps there's many situations that you can vary. So I can see a trend. And I also saw this trend when I was here on the it appears that for this system, what we have is a non-linear relationship. And because we have this non-linear relationship, I can see some equilibrium points that we can actually study. I can see some bifurcation points, I can see some equilibrium points that we can stay on and actually go deep and find out what is happening there. We can move from the theoretics to the analytics. For example, if you talk about Dr. Shoma will pointed to, if you want to do that stuff, we have to go back to that figure and do very fine step sizes. So if you do very fine step sizes, you'll be surprised that we can actually come up with a rate equation that determines the optimality of resources. So that's what the question is.
One of the questions is that
It's not really a question.
no, it's an analysis. No, what I'm talking about is that this is step side. I'm building advancing my no, but the thing is dropping.
No. That was the production of data. How is taking data?
It's on the same question.
Yeah, because if you look at this diagram, this is the height, and this is the direction. Which means initially, liquid metal is possible at this base. When you reach this point, it comes back and starts to the question. So if you start the first layer and second layer, actually, continue to guess. Because they will have seen if I do this video with Dr. Shoma, they will outline this high energy density. But still longer than this. Can you just make a point? We have wire, the machine goes on to lay another power, which is on the same time. The energy density that is coming is energy by 1 steps. For you to fit the previous one to the next one, it will be determined by the energy you are working. If the energy is not sufficient, we have what we call non-fusion or lack of fusion. So there is a minimum amount of energy. So what you see is that the ice will be relatively close to each other because the powder thickness or the liner that you are using. Because if you want to increase the rate, then you have to determine the speed at which you are doing the amount of layers. So if you want to change it's different from this of the thickness program. It's determined by the powder thickness, wider that you can see to the so you keep it same as you are ready to do the first one, the second one, thank you very much.
Thank you for your presentation. And also thank you for other colleagues that have contributed. Mine is just two things. One, the comment. Well, I look at the material. I thought the material and the practice. It looks very fast to break very, very hard. And I can see different applications in the cognitive engineering, especially most of the magnetic, magnetic device, and you use there. Those are conductivity and everything. It can also be used. Yes. Yes, I believe investors are here, and that's the beauty of them. Is when you do research, you will be able to send it out. So that we want to reinforce the federal government. Maybe Dr. Shoba, if you have a model, for this experiment, maybe you have developed a mathematical model, just like my prof said, because he's asking about the numerical, because it's the numerical method. So if you have deviates maybe from numerical, let's look at it intelligence system, whereby it can tell you at what level you have to pull, at what layer you need to go. Since you have different data, why not look at intelligence system?
I will see. I have data for the theoretical models. No sense. So with that data, I have all the sample data. Well, I've done a lot of experiments like some of them that we want to see. As I said, that theoretical sample, 150 samples is 150,000. So we can use data because I'm not going to represent all of them. Thank you very much. Yes, the paper for unified standardization. It's your turn now, and I think you are doing there's one question.
Somebody is mounting our international best practice.
You have to social them. Social them.
Okay. Now they will be social.
5,000.
Important tools for all industrial applications. Professor Jolo, Dr. Fono, myself, this is the brief summary of the outline. The first slide is about a brief summary of the manufacturing. Additive manufacturing has been given different names, as you can see on the right-hand side. Many people, depends on what you are doing, it's summarized. Cladding is under additive manufacturing, laser melting, selecting, laser melting, sintering, and so on and so forth. And what we can see in that basically represents a single track. There is a part called division, is the part that goes into the software when you first deposit the first layer. Then the big part is the one that is above the software. We have the heat source, which will be in forms of arc or will be in forms of beams, laser or there's other form of beams as we go on. What we feed in could be in form of powder or could be in form of wire. So you can see that there are always be a dilution from the substrate. Part of it is going to mix with the powder or the wire that we are using. The next slide shows us the breakdown of the heat source. As I've said, we have parts that is laser, electron beam, and if you are using wire arc methods, you can see the breakdown. And we have the feedstock that is either in powder. So the area where we are interested in is using lasers and other powder that is manufactured. There's other different forms of methods. Then the next slide. Yes, yesterday we listened a lot to wire arc additive manufacturing. So this slide shows us the comparison between the two in terms of cost. Which one is cheaper? Which is better than which one in particular? For example, in terms of cost, you can see that additive manufacturing using powder method is quite expensive compared to wire arc, which is relatively cheaper. In terms of quality, yes, it could be varied in terms of powder, because it depends on your heat source, you determine the quality what you have. But because of the advantage of resolution, which we are going to see in the next slide, the feedstock, then the net efficiency, how efficiency the process it is. The wire arc is much efficient than that of the powder bed because the material utilization is quite high when you use the hand. So you always try to finish the surface and get the benefit materials. Then recycling, yes. When you use powder bed, you can still recycle the product that you get out of it, but probably due to heat, heat treatment that has been taken place to the power. So it is better in this case to use wire in terms of recycling because virtually we are able to recycle everything when you're using powder. And so on and so forth, we can compare the two of them. Yes, this next slide shows us about bit rates, as I've said initially when we asked the question. Bit rate is very important. This additive manufacturing we are talking about, there are different types. Each one of them has an advantage and disadvantage. In the case of powder bed we are talking about, you can see the bit rate is quite slow, very low, but it has high resolution on the other side. It means that if you have a very small time object to build, it is better to use powder bed because you get a very high resolution. But if you have a big part to develop, wire arc additive manufacturing, you can see it at the other end, quite high. You can get a very high image, but it lost the resolution. That is, to get a very small part, use a wire arc is white. Then the next slide is about the standardization we are talking about. If we look at for example, my department, we carry out a lot of experiments. But before you do the experiment, we always inform ourselves to what is the standard at which we are working with, so that every other person can repeat the same thing and get the same result. This has not been fully done in additive manufacturing, because everybody is doing his own thing at different times. There's a lot of different types of additive manufacturing machines all over the world. So if you use Mr. A, you can get what is happening. So the idea of standardization is to make sure that we have a standard that anywhere we go, any type of machine that we are dealing with, we can take the same result. So additive manufacturing technology, that's the following advantage over the traditional short-acting methods. That is, the design EQKC is quite better. It's cost effective and so on. The standards are required to meet, of course, industry needs to have a standard before you want to go into the industry. If you don't have a standard from the striving, the end user also will benefit from it. The next slide talks about the rules of manufacturing standards. What are the rules? One, standard can be used for specifying requirements. Satisfied bodies typically referring to public available and standard standards. That is, the public can also make a reference to what they deal with, and industries are going to go in line with what has been specified. I itemized all the barriers that is associated with metal-based additive manufacturing. Limited material styles, that is, if you look at the powder they are using, it is of different grades, different distributions. So, which means before you can use a powder for additive manufacturing, you have to specify what is within which range are you going to use in order to achieve the same thing. Lack of process capability is a major problem. If you see what Dr. Sugar presented last, and you see the difference, you can see how that things look different, because one of the major problems is if you use a parameter A and repeat it again, you will not find the same thing. So very difficult manufacturing. Insufficient part accuracy, similar to what I've said. And so on. We can go on and see what are the barriers that is going against that. So challenges associated are also give this, not just to quickly round up. Yes, there are different organizations that are now working together to see how they can standardize additive manufacturing. One of them is American Society for Testing and Materials. I do attend their meetings when we the funny thing is that it's only Nigeria and South Africa are the only two countries that do participate whenever ASNTM goes on. So different bodies, as I can might have over there, are the ones that are now coming together. They now come together under a single umbrella and see that, okay, you are doing your own, this is doing this, let us all come together and have the same standard that everybody can follow for additive manufacturing. So this is the general structure of additive manufacturing standards that we came up with. Individuals have to fit in which area you fit in and provide or information. In my own area, where I'm interested in is in the case of parameters and the powder characteristics. How can you play with the powder? How can you play with the parameters of the user to see that is there information that we can generate? So, as I've said, our research area is in two: materials and processing. We are looking at parameters and looking at the powder. And how do we arrive at this? Our previous experiments have shown that if lasers that you are using for medicine, if you stand it directly on the surface of the powder, you get the perfect circle, the spot size. By the time the laser go to end,
what we see that the spherical shape at angle 45 will be formed. So A represents the original circle. You cannot work at 100 directly because reflection will come back and it will destroy that laser. So in most cases, when you are using laser, you have to see it in order to avoid being damaged. So the essence of that 5% removed from the 90 just to avoid. Then we go at 45. We discover that at B, you can see that the beams at different direction is more wider than the original one. So what is the implication of it? The implication is that a simple illustration is this. At 95, you can see welding is more or less like the same as at 95. To the best of my understanding. You are just building parts instead of so I use the welding to illustrate this. I use welding to illustrate this. In the original case, at 95%, you can see a spherical shape inside the structure. But when the laser moves to 45 degrees, you can see how the profile look like. When you move again at a tilted side, you can see. So which means when you are building parts in additive manufacturing, very, very high possibility that you will not be able to get a consistent, the same tracks. The issue is from our own view that a laser should be designed in such a way that the optical system that goes with the laser can modify the shape so that at every point that the laser is going to retain the same profile in order for us to be able to exist. What I just showed you, this is the parameter that I will use for that. And the beam spot is 1.37. When it has 65 degrees. But by the time you move, it has increased in size to nearly 1.94 at an angle of 45 degrees. So, meaning that if you are looking at the power density of the laser, which has a formula of laser power over the area of the spot, because the area of the spot has increased and you keep the same power, which is what is the power there? The laser power 61. Okay, 0.9 kilowatts. So the laser power that was used there is 900 watts. We use the same speed of 0.69 meter per second. So when you are working at this rate, what it translates to in terms of energy that are going to the system, it's not the same. Either you keep the same travel speed, you keep the laser power, but because the area has changed, then the power density, which is actually responsible for the melting, is not going to be exactly the same. So if you increase the area, you decrease the power density, as you can see there. If you make the area smaller, you increase the power density, and this has a great influence on the energy system. Well, if we succeed, our interest, we are able to establish that yes, changing in these parameters actually affects the bit rate. So the next stage is that what are the information you can provide in terms of parameters to standardize the system? And if you achieve that, these are some of the advantages that is applicable. Thank you very much.
Thank you for that. Actually, we are still the fact. It's for us to respond now. Questions? Yes. One. Two. Two persons. Okay. Three. And finally, last.
I just have to say about when I get so I think we should have an area here where you go from that micro level of the past, and that will improve manufacturing. So that when you lay it, it's very, very smooth and there's not a difference. So it's a suggestion.
Exactly, you are right. You are right. The spot of the laser that comes in, if you have a powder that the grain size is bigger than the spot of the laser, of course, it's not
That's it. So it is better you go to nano level, nanoparticles. Then the powder will at nano level. That will give you final products. So that then I just when I was here about additive manufacturing, I know that I saw subtractive manufacturing. Yes. And when you are there, it says traditional subtractive. I know that there is a traditional manufacturing. So what is the traditional subtractive manufacturing?
that should be relevant.
You put it in the slide.
There's an error.
I'm just trying to. The last you mentioned area power. That's when you increase the area and the power density will come down. Something like that. I don't know if you understand that.
Yes.
So that's not what normally is. I've been invoke this idea of modeling enough that there is a relationship.
Of course, there will be definitely.
I don't know if you have established that relationship between that power density and area.
There is an existing formula that relates to, and that is what we call the power density. Power on its own is a machine. When you have laser machine, you have the ability to adjust the speed. You can equally adjust the power, which is in watts. But power over the area of the size that goes in is what we call the power density.
You know you present the relationship, right? That's model. That model is what I'm interested in. That model that you need to see matter is
Thank you for the your slide 2. You talk about the comparison between our powder and wire. Where you are talking about comparison, on what is it the temperature? Let me give an example. For example, in the electrical application, if I want to compare things, for example, the of welding, the type of power, and or the iron. If I want to look at some metal, then what will be this temperature at which we throw in the so if you are saying powder and on what basis? What is the temperature at which value? Is it for high temperature object or for low? So that's where you can have comparison. That's my own.
Well, based on what I've shown, I think yes, it's okay. Let me just accept. Sir, I said yes. That's why I don't ask, because if you can let me know where when you make the definition of the people, yeah, I want to cite an example for you. If that example you don't go with the answer, if I have to use this laptop, for example, I have two methods. Either use powder or I use one. Why? You understand? What quantity of material did I use when I'm working with powder? And what quantity of materials did I use when I was using wire? Then that will determine, which I know what I'm talking about, that determines the cost in terms of cost. Does it make sense for me to go with wire, or does it make sense to go with powder? That's answer the question.
It's not that for example, to see the style, in fact, it's going to be good. If you are talking about that one, if it's another company, let's say electric welding, then the comparison might not be the same for that. So what I'm saying is that if the comparison is supposed to snap it to what you are really looking at, that's one of them.
I thank you very much, and I thank all the organization for this conference. Well, thank you very much for inviting me. I really do appreciate every paper present. The question now is that all this what we call it additive manufacturing. I'm from civil engineering. And my own question now is that I've not been listening to some whereas when I'm talking about additive engineering, additive manufacturing, or not calling additive construction. You see that as a civil engineer, you go to structure like I write this foundation code. Manufacturing or construction. When you are talking about roads, you talk about asphalt. Then when you are talking about building, you talk about concrete layers. Particularly when you are talking about ground foundation. This ground foundation is going to like 3 meters from 6 meters. You don't lay it once. You do it in layers. So, invite us.
Yes, you have done well. They actually preempted what I intend to say. Additive manufacturing is how we can go and construction. It's really practice now. And that is one of the reasons why I said we should all be here. If you Google additive manufacturing in construction, you see that there are different forms of it. And so when we're talking about standardization, it's simple, for example, you want to cast your smart. But you say that further crisis is not in doubt. But then, in all the discussion that we have had, we talk about the impact, the cost. What is very important is civil engineering. You design to specifications based on the applied rules. And that determines the fitness of your members. How you then cast the different working. So the civil engineers here, yes, we not discuss what video clip of construction where structural engineering has. So, well, let me say this that we have come to the end of this conference. Let's give us we started with boys, and we have finished the papers. Wait now. Yes. So I want to appreciate each and every one of us for attending this first international conference on additive manufacturing in Nigeria. It's the beginning. It's not going to be the end. I want to sincerely thank raw material and research development. The Lagos office, Mr. Abi, and engineer Obasi from Abuja office, and I brought some goodies from Abuja. And we are going to distribute that for also Manufacturers Association of Nigeria. Very respected, and they will have about this. You want to see your face, stand up now. Representing the Manufacturers Association on the organizing committee, but currently in Kano, attending the conference here. And we have our own people, the Addictive manufacturing group. Get to that because Addictive manufacturing transcends beyond engineering. That is why Dr. really write the book from time. And that's why Addictive manufacturing group, University of Lagos, not faculty of engineering and glorified faculty of engineering. That is the correct. So let them write down for a completion of all that are here. They remember, are we really here? Yes. Actually, this power of holding this conference for people render selfless. Because they are residents. When we reach out to Ministry of Industry, Trade and Investment, they have said that one of the I've been putting the idea of additive manufacturing this is for us to put that the promise to be out of us and to be well represented. Just about 1.5 weeks to the conference, all were no longer answered. I was told that the minister will be represented as one senior member of staff here, but here we are again. Right? So that is it. Again, I assure you that all these people that were presented during this conference will have proceedings. Raw Material Research and Development Council assured us. Yes. So we will have the presentation, and then we requested for a special journal. Raw Material Research and Development has a journal. So a special edition of that journal will publish all the papers that have been presented here. For the time frame, thank you very much. Then after this session, we're supposed to be your friend. But we want to put on record that those people who have attended this conference has something to show. So only those people who attended the minimum of 2 times will earn the certificate of attendance. Right? 2 times. 2 days. 2 days. We will have certificate of attendance. So I will distribute the certificate now. What applies to Nigeria for the countries? I'm coming to them because Dr. Cynthia Abiba is a special guest today. I'm coming to her because she's not supposed to be there. I called her yesterday. I requested her to come in here and then take part in roundtable discussion because of our wealth of experience and come to them because they participated both in the exhibition, yes, and the sponsorship. So it's a gradual process, right? So
Can I just stand up now?
And the you are all welcome. You receive.
So we brought him in. So we got him last night.
Thank you. We should be the digitalizing of this conference. Because again, we are going to discuss beyond now. Very, very important for very respected. Then we have wildlife system limited. Wildlife system limited, we don't hesitate because we take a road to have presentation for exhibition. We also showcase what they have. So I also want to thank them. Now, the roundtable discussion, that is where I am going. University always be part of this program for 2 days, the 1 and the 2. And yesterday I talked to Frank. You must talk to us. You have experience and manufacturing. There is no time for. Please join us. So it's good to join us for 1 day. And some of us will know whether or not to do it. I was in this laboratory in June in the class at University College. We were supposed to come in for this one, but because of costly performance, we couldn't come. But yesterday was online. And I spoke with him yesterday in the evening that he should join us for this roundtable discussion. It's also going to join us. Because I believe that at the end of this program, we must come up with robust communicate that you can from material research and development is here. The concept of going to ministry of industry and investment is transferred. They will represent government, but you can't get them. And so we are relying on raw material research and development. Being a government parastatal, that whatever we discuss here, you'll be able to resolve relevant. I can also think of honorable minutes, but then that is at a later stage. Now, for our roundtable discussion, we're going to have the privilege of having all of these people, Professor Doba from Beirut University, Professor Olatidoye from Atlanta University, we have Professor Ajibule from Unilag, Professor Amuna from Unilag, Dr. Ogo Naya from Unilag, we have Mr. Tokupo Abib, Raw Material Research and Development Council, Engineer Obasi, Raw Material Research and Development Council, Dr. Cynthia Abima. You want your digital officer to join us?
Yes.
So it was by your side. Very important for the flow of knowledge. Okay. That is where we begin. All right. Then we have Mr. Patrick Rule Model, right? From Man. And the secretaries would be Dr. Ochoba and Dr. Ayola. I will superintend that so, having said all of that, I will proceed to distribute this certificate. But then the faculty of University of Lagos and have plans to present to Raw Material Research and Development Council, I believe that's and Agricultural Association of Nigeria. I think please, somebody can join me here. This one is not very particular now, because there is no other. We have
There's something I hear back.
Well, it's not supposed to be here to be like my dear.
As you know, us. Dr. Shoba,
Because it's a contact person and doctor in we are not having time. It is Monday. Dr. Park is qualified. Yes. Yes. I think that's what they can see this. Yes, that books are seriously. Mercy of God. Of God. But God is in control. Yeah. So very nice. So having said that, okay. Just a second. Chairman of AM, chairman of AM and the law. Come and get there with us. Come and get there. Oh, that's the governor. What's young here? Yeah, let me say this one. I want to thank Dr. Cynthia to Vasily. Vasily is the CEO of Nigeria Poultry Limited. That right? At the time we started this, program, it was very, very hard. And I contacted him. Indeed, he received a delegation of our team in his office at Porta. This has been suited. They are not the good people. They are from Porta. And on Monday, when Dr. Cynthia and Human Resource Officer, Dennis came, it took them how many hours to make program? About 4 hours only. So, requesting her to come was an Herculean task. But all the same, she gave us that privilege to have. Let's all do that. We came with somebody high-powered digital. So our table discussion today, you can ensure that it's going to be survive. So we appreciate you and we appreciate Mr. Vasily. I do the call with him, but he is not in Nigeria now. He's outside the country. But we pray that we get us safely and in good health and sound mind. So after today, we will follow up with the industry partners, and we'll try as much as possible to ensure that additive manufacturing is well rooted in Nigeria. That is the way to go, and that is the way that other countries are going. So thank you for coming. Now we should have. I think we should have a proof of program, so that at least this one is we are more than one at the initial stage. So on that note, I don't know whether Mr. you want to say something. If you want to say something, so that we know. Of course, while you are out there, I talked about the proceedings of this conference, and then talk about the publication of the paper that was presented. So you can say something along that line, and then encourage people to also do their business data, research, development, and do that. And then what material research is having a talk. Oh, thank you.
It's a very wonderful experience. I thank all of us. So wonderful. I say myself and my team. Very thankful for that. When I look at the research in we are supposed to be at the epicenter of this kind of events, and we are happy we are here. And that we are promised we want this thing to be, we want to sustain it, whatever it takes. We shall always be that. It's a whole experience for me being here. I stayed with the Professor and then that was happening from there, and like you can see the people trying to go to come over this. And we have started developing what we can call an additive manufacturing setup in Nigeria. And that's what's that putting? It's national space development. We have gone far, so because we are not even started. So we have to go back there and inform our CEO that we have a lot to kind of having will be talking with the University of Lagos in this case. Thank you. We also have a center in Lagos. Not of that side, my own office. We have we maintain a project office in Lagos. Completion something science. Where myself and overseer consequence that we should also create a center in Lagos which are going to let the people that you are already talking to like us and you have to do something about it. It's going to happen. So friendly, so fast. It's a very good experience of time. What we do that. Thank you so much. Very thankful. Thank you very much. What is it? I can tell you.
I can tell you. So, we want somebody who is so inspired. Come and give us a good prayer. You must post this thing up. So, while we remain, you do the need to respect to all taking discussion. You take your food, well, anywhere you want to go in the rest of Lagos. We have Magun for
Class 1, yes.
you can go anywhere, just brand people running around when you are tired. And then thank you very much. What was closing prayer? Okay,
Much right.
oh Lord, we are grateful, Lord. We are grateful. Oh Lord, hallelujah. For this wonderful family. At this time, you have entered this part. Thank you for everyone from far and near that you have progressing. Thank you for the organizers. Thank you for everyone that is one way or the other has been involved in this process of this program. We give God the glory in Jesus' name. But I also want to thank you for the outcome and some of the props that are coming of this 3D program. Some of the policies that are being some of the moves that are taken for future advancement. We ask the Lord God that you make them possible in Jesus' name. That's for strength, grace, and life to advance in all what you started. We ask the Lord God that you will engrave and increase us with more privileges, even the one that we have not seen as of now, to make this gathering a more profitable gathering in the future in Jesus' name. Amen. As we gather here, Lord, we also commit the country to everyone. There are several areas where there is need for the touch, both financially, spiritually, materially. Lord, we ask for divine assistance from above that will make it possible in Jesus' name. Thank you. Thank you for your faithfulness. But we go back and find this mission that you go with us in Jesus' name. What to pray particularly for Dr. Faraday and how his team, as well as the visitors, that Lord, you will empower them, you will equip them, and you will perfect their concerns in Jesus' name. But even at this period of strike, there are so many needs that we have individually. We are praying, Lord, that you meet all our needs in Jesus' name. Thank you, Lord. In Jesus' name, we are praying.